On at home, welcome to a very windy evening coming to you from Cambridge University Astronomy. As you've probably guessed, if you've looked outside at all, there's not going to be any observing. We don't want to put any of our observers at risk of blowing away. So we are just going to have a talk from our headline speaker this week. So I'm here with Dr. Robin Catchpole, who's going to tell us all about doing astronomy in Antarctica. So over to you, Robin.
Good. Well, thanks, Matt. Antarctica, as you probably realize, is a desert. So one of the coldest, driest places on Earth, making it an ideal place to do astronomy. But before we start, I just thought I would do a little recap about to introduce Antarctica. Now, we all know the Earth goes around the sun, and we all know the Earth has a tilted axis of rotation. So that's the way it is in the universe, if you like. And we can also represent that from a geocentric, an Earth-centered point of view, where the sky rotates once a day, and during the course of the year, the sun makes its way along the ecliptic. And so we can now go to a little place on the surface of the Earth. Here we are. So Z is straight overhead. P is the direction of the pole, and sun somewhere over here. And of course, as you know, during the course of the year in midsummer, the sun rises in the northwest, in the northeast, and sets in the northwest. And in midwinter, it's somewhere down in the southeast and sets in the southwest. So we're all used to those things. So let us just think what happens when we go to the pole. So here we have the same arrangement we saw just now. This is somewhere at some latitude, fairly high latitude. And now let's move the pole towards the zenith, which is equivalent to us heading to the North Pole. And of course, as we do, the equator, which is the bit that rotates once a day, goes down to fit on the horizon. And there are times when the sun is above the horizon, rising in the east and setting in the west. And then there are times when it's below. So if we were at the North Pole, and it's the same at the South Pole, in the middle of summer, then the sun would rotate right around the sky at a constant altitude of about 23 degrees. And then as the season progressed, it would rotate ever lower and lower till at the equinox, it would be running right around the equator. And then in the middle of winter, it would be run right around the sky, always 23 degrees below the horizon. And so we would be in total darkness. But people forget that the moon, of course, still comes up in the skies. So when it's midwinter at the pole, when it is full moon, the moon is on the other side of the ecliptic, and so is at the sun's midsummer position, but it can do better than that because of the ecliptic and the moon's orbit being tilted by 5 degrees, and the full moon can be 28 degrees above the horizon. Well, that's a very quick introduction to what it is what the skies are like at the poles. And talking of the sun and the moon, we had an eclipse that was visible, a total eclipse in Antarctica at the beginning of December last year, which is coming up to, fairly close. It's well into summer in the Antarctic. And indeed, here we are very close, physically close, within a kilometer of the South Pole. And you can see these 4-minute interval exposures during the eclipse, which was only partial at the South Pole. You can see how the sun was moving horizontally around the sky. Now, talking of eclipses, if you're going to go to an eclipse in Antarctica or in the Arctic for that matter, you'd better plan yourself pretty well and organize yourselves well. Otherwise, this is what happened back in 2003 at this total eclipse. Just as totality came, one of the observers discovered there was somebody immediately in his line of sight towards the sun. which was skimming the horizon at that stage. So why would we want to observe from Antarctica? Very briefly, the sky is clear. It's 65% of the time it's photometric. At the places where we like to observe, the wind speeds are extremely low. The atmosphere is very cold, and which helps with infrared observation, and the seeing is extremely good. The atmosphere is extremely dry. This is 0.14 millimeters of precipitable water vapor. And in winter, it can be 10 times lower. If you go to Chile or somewhere, you will find it's about 1 millimeter. So it's almost 10 times as good as the Atacama Desert. And in the UK, it can be 20 millimeters or more. It's very stable, the transparency, and the boundary layer, which is the layer, it's the upper layer in which turbulence occurs in our where the heat is being exchanged from the ground to the atmosphere, which may be 500 or maybe a kilometer or so at our kind of latitudes, can maybe as little as 11 meters above the surface, which means you can get above most of the seeing. And of course, there are long periods of uninterrupted darkness, months at a time. But there are, of course, problems. The working conditions are extremely hostile for people and instruments, with temperatures ranging from -25 to maybe -80 or even colder in winter. And there is the ever-present, despite the dryness, this snow dust that tends to accumulate on telescopes, the surface of telescopes, and one has to deal with that. There is a long and expensive supply chain to get to the telescopes, and you can't, well, in theory, you might say you could see half the entire night sky, but in practice, maybe only a third, because you can't observe right down to the horizon. And of course, there is the auroral glow. And of course, there are long periods of daylight, although for some observations, infrared and longer wavelengths can be done during daylight. Now, the most promising places for observations are these high points, these domes. These are the highest points in Antarctica. And these are places where the wind speeds are very low. The wind is the air is settling and then pouring off the edge of Antarctica, giving very high wind speeds around the perimeter. And these are the sites of observatories. So we're going to now visit the observatories. Oh, incidentally, you'll see Dome A, Dome B is actually here, but nobody's there. Dome C is here, but there's no D or E. There is then Dome F, which is actually, it's not, you might say it's Dome F for F, but it's actually a Japanese site. So it's the Fuji site. It's Dome F for Fuji. And oopsie, oh no, we've jumped ahead there. Yes, this is the place where the Japanese have their weather station, and it's about 1,000 kilometers from their base. They have plans for a 2.5 meter infrared telescope, but as far as I can see, nothing has actually been built at that site so far. So let's move on to Ridge A, which is very close to Dome A, and an analysis of weather records and satellite observations suggests this might actually be the very best of all places for actually undertaking observations. And there is a joint New Zealand American activities going on at this location. There are some of the coldest temperatures ever recorded, -93 degrees centigrade, were recorded nearby Ridge A. And it's a height of about 4,000 meters or so. And what we see here, you see this yellow box with Plato written on it. This is a New Zealand experiment, and it consists of a communication center so that it can communicate with satellites. It has all sky cameras, and it also has weather monitoring facilities. Now, its other function, and maybe its main function, is as a power supply. And it has a set of solar panels that go with it here. And it also has a diesel motor that will supply power during the dark times when there's no sun. And in this case, it's powering this thing that looks like some kind of barbecue device here, is called the heat experiment. And we'll have a little closer look at this in the next slide. And heat, Antarctica is full of acronyms. This is the High Elevation Antarctic Terahertz Telescope. And essentially this works between 600 and 150 microns. This is a steerable mirror that reflects light, the sky, onto this fixed concave mirror, focusing onto the secondary here and then into the measuring device, the detection system here. So that's basic, and then it's covered up with the cover and it looks at the sky through a window. And the prime task of this heat experiment is to observe the galaxy, the galactic plane, at wavelengths where the lines of carbon appear. And this is an example, an early example of the scan, a strip of scan. The white blobs, white lines here correspond to regions of sky that have not been observed. So here we are from the center of our galaxy here, looking out between the longitudes in this scan of 304 to 340 degrees. So we're looking through these various spiral arms, and not only do we see the emission from the carbon molecules here and carbon atoms, but we have velocity information, so we can sort out the dynamics and decide which spiral arms the radiation's coming from. Carbon is a proxy for the heavy elements, and so this tells us a lot about star formation, which is the main project that's being done here. So let us now move on from Ridge A to Dome A, and this is the region where the Chinese have their observatory, and they're about 1,300 kilometers from their shore base here. And the Chinese have really done, in my opinion, the most advanced as far as exploiting Antarctica. And the very first camera that they erected in about 2008 is this array of four 14.5 centimeter wide field cameras that had a 20 square degree field. And you will see they're also using a version of the Plato power supply, which provides power for these things. And these were deployed in 2008 and were used until about 2012. Very good for finding variable stars and also tracking space debris. So that was their main function. Since then, they have been developing this next generation of 350 centimeter Schmidt telescopes. And here we see one of them, alt-azimuth mount, being built and assembled in China. And this was called AST-1. It was deployed in about January 2012. And the last one is supposed to be being deployed this year. Oh gosh, yes, time is racing by as ever. So here it is being deployed at their location, and here it is with its weather protection on and then here under this is a kind of cover. It uses nitrogen to keep the optics dry and heating to keep the snow dust off the objective. This is another relatively small 30 centimeter telescope, the Antarctic Bright Star Survey Telescope, that is being deployed in 2016. And what's interesting about this is that it's on top of a tower. And this is to overcome the ground effect seeing, so we can get the actual seeing down tenths of a second of arc or so. And this is certainly a precursor for what they propose, which is this Kunlun Dark Universe Survey Telescope, which is a 2.5 meter telescope that they hope to mount on a 15-meter tower. This is currently awaiting funding, and you will see it is a wide field instrument. You see the optical alignment, secondary here, tertiary here, a kind of coude arrangement, which allows you to have instruments that are not moved around the sky, that can be maintained in a stable atmosphere. And this telescope is very much used for proposed for exoplanet research. This brings us on to Dome C, the Concordia Dome, which is a French-Italian and now has overwintering facilities, which the other doesn't. This is also the site of the EPIC A ice core, one of those cores that tells us about the climate for the last 900,000 years or so. And they have a variety of instruments, including this infrared telescope, International Robotic Infrared Telescope. That's what IRAT stands for. And you'll see it actually, the detectors are held at only about between 0.25 degrees above absolute zero and 4 degrees K. And it's designed to work between 1 and 25 microns. You'll see it's got a filter on the front here for observing the sun. And this is, interestingly enough, it's a film of polyethylene film, 150 microns in diameter, with a white side and a dark side. And it's actually used for protection of boats and agricultural projects. And its white side reflects in a non-specular way, so it's not like a mirror, but they claim that because it's such an efficient reflector of radiation, it only gets to a temperature about 5 degrees K above the environment. So there it is. It has to be cooled, actively cooled, and by refrigerators. And the refrigeration system, the other end of the refrigeration system, warms the place where it operates, is controlled from. This is a 40 centimeter telescope, also used for looking for exoplanets. It has all kinds of devices to keep the mirrors warm, to evaporate the snow dust, and the filter wheels and photometers are kept in a isolated, relatively warmed. They maintain it maybe up to -30 or something, temperatures at which electronics work. And here is some of the exoplanet candidates that have been observed in this very good photometric environment. And I'm not going to say anything about exoplanets today. I'm sure we've all heard lots about them because we don't have time. And I want to move on to the South Pole, which is very much an American sphere of influence. And here is a view from the air of the South Pole station. The actual South Pole is somewhere here, but of course, everything moves. The ice moves about 9 meters per year here. So one's busy drifting over the South Pole. So anyway, here we are. This is the accommodation area. There is the actual South Pole, the stores. And we want to look in this dark area on the left-hand side of the runway. And we see a number of different systems, essentially telescopes looking at the sky or astronomical activities. And the first one, which is called Mappo, is actually, this was one of the earliest, built here in 1994. It was actually an early cosmic ray observatory, and it now acts as a kind of workshop operation centers for the other things here. And next to it, we have the BICEP and the South Pole Telescope. BICEP here was used for mapping the cosmic radiation background and came up with the false discovery of possible polarization that was thought to arise from gravitational waves in the early universe, but turned out to be dust in our own atmosphere. At the other end here, we have the South Pole Telescope, which is works in the millimeter region and does cosmological observation. It's also part of the Event Horizon Telescope, this telescope to bring together all these millimeter arrays, and they can work as one coherent telescope with the scale on the size of the Earth. And you will remember, although the South Pole Telescope was below the horizon, that this Event Horizon Telescope was the thing that managed to map the black holes for us. So that brings us to perhaps one of the most unusual and exciting projects here, which is the Ice Cube. Now, the Ice Cube is, here it is, Ice Cube at the center. There are the other telescopes there. This Ice Cube telescope occupies a square kilometer here and consists of an array of these 5,160 detectors on 86 cables that are lowered nearly over 2 kilometers below the surface. And they act as a detector inside the translucent ice that starts 1.5 kilometers below the surface and goes down for another kilometer, occupying a cubic kilometer of ice, these strings of photo cathodes that spot the radiation of particles that move through the ice. And on top is the region. The cables all come up here to the center here. And of course, this thing has to be jacked up. Now, in order to build this, what they had to do was drill these holes, and they drilled them using hot water that are going down nearly 2.5 kilometers. And this is one of the photomultipliers. This is the photomultiplier at the bottom here, and the electronics here, and they are attached to the cable and lowered into the tube. And when a relativistic particle goes through, in this case a muon, which is like a heavy electron, traveling from this size, it is going faster than the speed of light in ice. And so it emits Cherenkov, a sort of cone of radiation that is detected by the photomultipliers. And here, these blobs correspond to the photomultipliers that were triggered, and the diameter of the blob corresponds to the brightness of the flash. This is a muon, which is produced by a neutrino, and this is what's called a high-energy starting event, when maybe a different sort of neutrino, an electron or a Tor neutrino, as opposed to a muon neutrino, strikes a particle and causes one of these events. And you can see, we can measure the direction very accurately here of the travel of the particle, but not so accurately here. Now, the amazing thing about this is that basically we only want to observe things that have come up from below the ground. So here's Ice Cube in the southern hemisphere. Here's a very high energy cosmic ray, strikes a particle in the Earth's atmosphere, or oxygen or something. And one of the products is a neutrino that then strikes another electron or oxygen or hydrogen atom here and emits a muon, if it's a muon neutrino, that passes through Ice Cube and we detect. What we want to avoid are the cosmic ray neutrinos and muons that come from above us. Some of those are filtered out by the ice cube. And what we're really interested in are these cosmic ray neutrinos that also will come through and give us our muons. And just to give you a feel for what we are seeing, cosmic rays coming down from above amount to about 100,000 million detections a year. Cosmic rays striking the opposite side of the Earth, very high energy ones, much higher energy than a lot of these, maybe 100,000 per year. And these raw cosmic neutrinos, only a few a year. And I'm very clear that I'm coming close to the end, so I'm going to wind up this soon. And here, this was published in August 2015, shows us these red blobs correspond to these unique neutrinos that maybe have energies of 10 to the 12 electron volts. That's 10 million electron volts. The rest mass of the neutrino is less than 1 electron volt. So they have this high energy from their high velocity. And the really exciting thing back in September 2017 was this detection. And this was a single neutrino with an energy of 3 times 10 to the 14 electron volts. And we could see the direction in which it came. And it was possible to specify that direction in the sky, and it corresponded to the direction of a blazar. That's an active galaxy that was undergoing a flare. And that flaring was detected in gamma rays by the Fermi satellite. And you will see here all kinds of detections that were made of this flaring event that was detected as a neutrino. Now, since then, an analysis of about 10 years worth of neutrino data from cosmic rays, as opposed to the much higher energy neutrinos from individual neutrino events, has shown a significant peak in the direction of the closest active galaxy to us, NGC 1068. So neutrino astronomy has, in a sense, come of age. And I'm going to stop at this point. I'm just going to say that there is a proposal now to increase the size of this telescope, this neutrino telescope. There's the little detector. This is the snowy surface up here, from 1 cubic kilometer to about 8 cubic kilometers. And there will be a steady upgrading from the first upgrading will be in 2024, and they hope that this 8 cubic kilometer will be finished in 2032. I just want to say one last thing about this. I promise, Matt, is my last slide, is the other thing, astronomical activity that's going on in the Antarctic is the discovery of meteorites. As you can imagine, a meteorite, especially the exciting black carbonaceous chondrites sitting on a snowpack, is pretty conspicuous. And we are helped by the fact that the snow moves in the Antarctic. When it comes up against a mountain, it rises up, and then we have what's called a sublimation surface, where essentially the ice evaporates and it leaves behind all the rocks that it has incorporated. So it's a great place for meteorites. So, Matt, I think I will be good and stop there, only having overrun by 3 minutes. Okay, I'll stop sharing at this point.
Thank you so much, Robin. Three minutes is a personal record.
That is a personal best, yes. And
thank you so much. If anyone has any questions for Robin, do pop them down there in the chat. It's fascinating stuff. Do you think, if you had the chance to go to Antarctica, do you think you would go?
Oh, yes, I would. I would love to go. I have friends at British Antarctic Survey who've been, and in fact, other astronomer friends of mine were actually shipwrecked. Well, I have 2 friends one was shipwrecked not in Antarctica. One was, yes. Their cruise ship struck a rock and they had to be taken onto another ship.
That would make for a good story. I like that.
Yeah.
Wonderful. Yeah. I think there's a bit of a delay in the chat, so I can't see any questions coming through. So I think the best thing to do is to say thank you very much, Robin, for that fascinating talk. Really great to hear about all the goings on down there. So yeah, we do these talks every Wednesday through till the end of March. So we will be here this time next week with a talk from Sophie Kudmani, who's doing a talk all about supermassive black holes. So we will see you then.
So ask her about where the neutrinos come from.
Bye.
Good, thank you.